We are on page number 12 of the notes. AC circuit containing only an inductor. AC circuit containing only an inductor. So now I am talking about that circuit, that AC circuit in which we have only one component, and that component is inductor. So what will be the circuit diagram of this circuit? It will be like this. It is an inductor. E is equal to E naught sine omega t. E naught sine omega t, and what is this? This is L. L is inductor. Now, we always take one terminal as the positive terminal and another terminal as negative terminal of any voltage source or battery. So we are taking this terminal as positive terminal and this terminal as negative terminal, and the voltage drop across an inductor is voltage drop across an inductor is L di by dt. Okay, see, like we have a resistance is R, and if we say that current I is flowing through this resistance, then what will be the voltage drop across this resistance? As per Ohm's law, voltage drop across this resistance will be I into R. In the same way, when we have an inductor, then voltage drop across this inductor, if current I is flowing through this and the value of inductance is L, then voltage drop across this inductance will be L di by dt. It was shown in the last chapter, electromagnetic induction, that voltage drop across an inductor is L di by dt. So now there are two rules. Kirchhoff has given two rules in current electricity, that chapter which I have not covered that chapter, but let us discuss what is this Kirchhoff's voltage law. Kirchhoff's voltage law is commonly known as KVL. So I'm explaining what is Kirchhoff's voltage law. Kirchhoff's voltage law is just like this. Like we have a resistance R, we have another resistance R, R1 and R2, and we have a DC voltage source. We have a DC voltage source like this, V. This one is this, a battery is represented by parallel lines, by a set of parallel lines. So the bigger line is positive terminal and the smaller line is negative terminal. So it's a rule that current always goes from the positive terminal and it goes to the negative terminal, completing the path of the circuit. So if this voltage source is delivering current I, then current I is coming from this positive terminal, it is going in this resistance R1, then current I will go in this resistance R2, because in series current always remains the same. So current I will go in this resistance and current I will go in this resistance also. And after going in these two resistances, current will return to the negative terminal. So this is a normal circuit where we have only two resistances. So how do we apply Kirchhoff's voltage law, KVL? We always start from this point, or any point whichever you want. If I say that I am starting from this point, this is A, B, this one is C, this one is D, and this one is A. So if I say like this, KVL in the loop apply KVL in the loop A, B, C, D, A, in the loop A, B, C, D, A. Apply KVL in the loop A, B, C, D, A. Then we have to move. We have to move from A to B. We have to move from A to B, then B to C, then C to D, then D to A. So while moving from A to B, there is no component. Okay. While moving from B to C, there are two components. So we are moving from B to C and current is also going in the same direction. Then voltage drop will be I into R1 because this is Kirchhoff's voltage law. So we are going to take only voltages. So I into R1, I R1 plus I into R2 because again another component is there. So voltage drop in this component will be I into R2. I into R2. So we have completed this path B to C. Now we will move from C to D. So from C to D there are no components. After that we are going from D to A. While going from D to A we don't have any resistance. We have a voltage source, and in a voltage source and when we have a voltage source, then in our path the terminal which comes first, we consider that terminal as the we consider that terminal. Okay, so we have moved from A to B, then from B to C there are two components. So voltage drop is IR1 plus IR2. Sorry. Then from C to D there are no components. Then from D to A there is a voltage source, and in our path we are meeting this negative terminal first. So we will write it like minus V. And now we have reached point A. Minus V is equal to 0. So Kirchhoff's voltage law states that whenever we move in a closed loop, whenever we move in a closed circuit, then the sum of all the voltages across a loop is always equal to 0. All right, is this clear to you? And from here I can calculate the value of this I R1 plus R2. Minus V is here. If we take it to the right hand side, it will become plus V. So I will be equal to V upon R1 plus R2. Tell me, Anusha, is this clear to you till now? Is this clear to you till now?
Yes.
Okay. Sorry?
Still writing, sir.
Okay. Done?
One second, just writing.
Okay. Now, so this was KVL. Now I'm going to apply this KVL in this small circuit. So in this circuit we have only one component, and that component is an inductor. So now I am going to write here that apply KVL means Kirchhoff's voltage law in this circuit. Apply KVL in this circuit. So current always leaves from the positive terminal and goes towards the negative terminal, completing the circuit. So current I will go here, and then current will come into the negative terminal. So can I erase this one if it is not required?
I didn't understand this one.
Okay, no problem. I am going to explain it again. Okay, now we have two types of laws. One is Kirchhoff's current law and one is Kirchhoff's voltage law. So Kirchhoff's voltage law states that the algebraic sum of all the voltages in a closed circuit is always equal to 0. Algebraic sum of all the components in a closed circuit is always equal to 0. Look, if I have this circuit A, B, C, D, A, if I have this circuit, I have three components in this circuit. One is this voltage source, one is resistance R1, another is resistance R2. So Kirchhoff's voltage law states that the algebraic sum means total of all the voltages in a circuit is equal to 0. Okay, Anusha, wait for 1 minute.
Daddy. Daddy.
Wait. So I have three components here. One is this voltage source V, and one is this resistance R1, one is this resistance R2. This voltage source V is delivering current I. So the rule is this: current always leaves from the positive terminal and goes towards the negative terminal. So how do we apply Kirchhoff's voltage law? I am writing like this: apply KVL in the loop ABCDA. So I am moving from A to B. There are no components. There is no component. A to B is a straight wire. There is no component connected in this path. Now I am going from first A to B, then I will go from B to C. B to C. So current is I, resistance is R1. I R1, then I R2. So what I have written, I R1 plus I R2, because the algebraic sum of all the voltages, so what will be the voltage drop in a resistance? Voltage drop in a resistance is equal to I into R. So resistance is R1, that's why I have taken IR1. Resistance is R2, that's why I have taken IR2. IR1 plus IR2. After that, I am moving from C to D, no component, then D to E, one component, voltage source. So when I move from D to A, then I am encountering with this negative terminal first. So I will take minus V. If there would have been positive terminal here, then I would have written plus V here. Okay, so IR1 plus IR2, then negative terminal is striking first, then minus V is equal to 0, because I have reached now this point A from where I have started. Is this clear? Algebraic sum of all the voltages in a closed loop is 0. Clear?
Yeah.
Okay, so from here I can calculate current if voltage is given. If current is given, I can calculate the voltage. So this is Kirchhoff's voltage law. I am applying the same law here in this circuit, AC circuit containing only an inductor. So this was just to explain you what is Kirchhoff's voltage law all about. Now I am going to apply this law here. So that's why I am going to erase this one. Apply KVL in this circuit. So I am starting from this point, no component, no component, no component. Now the component is inductance. And what is the voltage drop across an inductance? Voltage drop across an inductance is L di by dt. L, like in resistance it is I into R. In the same way, the voltage drop across an inductance is L di by dt. After that, L di by dt. After that, I am completing the path like this, and now I am encountering the negative terminal first. So I will write minus E. Minus E is equal to 0. Minus E is equal to 0. What is my motive? What is our motive in this topic? In this topic, we have E is equal to E naught sine omega t, and with the help of this EMF, I am going to calculate the current I. Okay, so L di by dt minus E is equal to 0. Then from here, E is equal to minus E is equal to minus L di by dt. We will cut down this negative from negative. What is E? E is E naught sine omega t is equal to L di by dt is equal to L di by dt. Di is equal to E naught upon L sine omega t dt. Di is equal to E naught upon L sine omega t dt. Now integrating, we are integrating this equation. Integrating. Now integration of di is equal to integration of E naught upon L sine omega t dt. Now E naught upon L is a constant. We can take it out. We can take it out of this integration sign. So integration of di is I is equal to E naught upon L integration sine omega t dt. Now if I integrate this sine omega t, then integration of sine theta is minus cos theta. So I is equal to E naught upon L sine theta is minus cos theta, that is minus cos omega t, because the variable here is t, so we are integrating it with respect to t. So sine omega t's integration is minus cos omega t. Now I am going to differentiate omega t, and differential of omega t is omega, then we are going to divide it by omega, so upon omega plus constant. Now I is equal to minus E naught upon omega L cos omega t plus constant. Now tell me, is that clear to you till now?
Yes, 1, 2, 3.
Okay. Done?
Hello, sir.
Complete it.
You know that how much is I lost my internet connection.
Okay.
Yeah, I'm done.
Okay. So I is equal to minus E naught upon omega L cos omega t. Now we are on page number 13, and some theory is written over there. I am reading it for you. As the applied EMF is sinusoidal, we expect the current also to be sinusoidal. Thus, the average of current I must be 0 over a time period. Now, the average of cos omega t is 0 over a time period, hence the integration constant in the above equation, must be 0. Look, what is written? This E naught is peak value of EMF, maximum value of EMF. Omega is angular velocity. L is the value of inductance. So E naught, omega, L, everything, it is constant. And cos, the standard graph of cos theta, omega t is what? Omega t is nothing but theta. So the standard graph of cos theta is like this. The standard graph of cos theta is like this. And this one is 0. And this one is pi by 2. 0, pi by 2. This one is 3 pi by 2. No, sorry. 0, pi by 2, pi, 3 pi by 2. And this one is 2 pi. So we can see that this cos omega t, the average value of cos omega t over a complete cycle of 2 pi is 0. So the average value of cos omega t is 0. Okay. Why it is 0? Because we have one positive half cycle onto the right positive half cycle. This one is left positive half cycle. This one is left positive half cycle, right positive half cycle. This one is left negative half cycle. This one is right negative half cycle. So this one is positive, this one is negative. Sum of both of them 0. This one is positive, this one is negative. Sum of both of them is 0. So the total sum of one complete cycle of cos is 0. Okay. So and I, what is this? I is current, and current, alternating current is always, alternating current depends on sine theta. So alternating current also depends on sine theta, and the average value of sine theta over a complete cycle is also 0. Average value of sine theta is also 0 over a complete cycle, and average value of cos theta is also 0. That's why its average value is 0, so this constant must also be equal to 0. So you have to write only one line. Since the average value of cos omega t and I, in the bracket we have to write which depends on sine omega t. Since the average value of cos omega t and I, which depends on sine omega t, is 0 for a cycle, 0 for a cycle. So this I is going to be 0, this cos omega t is going to be 0, that's why this constant will also be equal to 0. Therefore, constant of integration is equal to 0. So I is equal to minus E naught upon omega L cos omega t, and in place of that constant we can write it 0. Is that clear to you till now?
Yes.
Okay. Okay, and we know that sine theta is equal to cos 90 minus theta, and cos theta is equal to sine 90 minus theta. So I is equal to minus E naught upon omega L sine 90 minus theta. Why I have converted this cos into sine? Because EMF depends on sine theta, so I want that current should also depend on sine theta, so that we can calculate the relation between E and I. That's why I have converted this cos into sine. So cos theta can be written as sine 90 minus theta. Now I want to remove this negative sign. So what I will do, I will take this negative sign common in this bracket. Within this bracket, I will take minus sign common. So I is equal to minus E naught upon omega L sine, I will take this negative sign common, it is omega t minus pi by 2 sine minus theta is equal to minus sine theta. So I will take this negative sign outside the bracket. One negative sign is here and one negative sign will come outside the bracket, because sine minus theta is equal to minus sine theta. So I will be equal to E naught upon omega L sine omega t minus pi by 2. Omega t minus pi by 2. And this one is E naught upon I will write E naught upon omega L as I naught. In this case, I naught. I is equal to I naught sine omega t minus pi by 2. Omega t minus pi by 2. So, where I naught is equal to E naught upon omega L. I naught is equal to E naught upon omega L. So what this relation of current tells us, EMF is E is equal to E naught sine omega t, and current is I is equal to I naught sine omega t minus pi by 2. It means that current is 90 degree behind the voltage. It means that current lags behind the EMF by 90 degree. The statement is clear to you? Is this clear what I am saying? Current is 90 degree behind this angle. Omega t is angle. So there E is equal to E naught sine omega t is written in that diagram. And here we are getting I is equal to I naught sine omega t minus pi by 2. If we correlate it, if we compare it with what we have done in pure resistive circuit, what we will see in that resistive circuit, E is equal to E naught sine omega t, And what we have derived? We have derived I is equal to I naught sine omega t. So EMF is also having the angle as omega t, and current is also having angle as omega t. So both are in same phase. But in this case, in inductor's case, EMF is E naught sine omega t, means angle is omega t, and current is I is equal to I naught sine omega t minus pi by 2. It means that current is lagging behind the voltage by pi by 2. Is this clear to you? Are you there? Is this clear to you?
Yes, sir.
Okay. It means that current is lagging behind the voltage by pi by 2. By pi by 2. Okay. Anuja, please give me 2 minutes. I am coming back. Okay, now, so thus in an inductive circuit, the current lags behind the voltage in phase by 90 degree. So we will draw two types of diagrams here. One is graph between E and I versus omega t, uh, and another one is phasor diagram for an inductive AC circuit. E comma I, and on x-axis we have omega t. This one is 0, this one is pi by 2, this one is pi, this one is 3 pi by 2, and this one is 2 pi. Okay, now this is E. This is E because E is E naught sine omega t. E is E naught sine omega t. Now, what about this I? Anusha, are you listening?
Yes, I'm just drawing.
Okay, okay. So, EMF is E naught sine omega t, and current is I naught sine omega t, and current is I is equal to I naught sine omega t minus pi by 2. Minus pi by 2 is current is lagging behind the voltage by pi by 2. It means that EMF has already started from point 0, but current will start from point pi by 2 because current will start late. Current will start late. How much late? By pi by 2. Current is late by pi by 2. So current will start from here, like this. Like this. So this is I. It means that current is late by pi by 2. So this is graph between E and I. Graph between E and I versus omega t. Graph between E and I versus omega t. And then secondly, we will have to draw phasor diagram. We are going to draw phasor diagram. What is phasor diagram? Phasor diagram can also be drawn with the help of these equations. With the help of these equations. How? Just see. In phasor diagram, whenever we draw a graph between E and I versus omega t, then omega t I take it on the x-axis and E and I take it on the y-axis. But for phasor diagram, we take x on x-axis and y on y-axis. So here it is x and here it is y, x and y. Now, EMF is like this. We always draw EMF in the first quadrant by a straight line. So EMF is like this. The maximum value of EMF is E naught, and current is 90 degree. Current is pi by 2 behind the EMF. So current will be like this. We always note that the magnitude of this, we always note that the value of this E naught is always greater than I naught. E naught is always greater than I naught. Okay, so that's why I have drawn a big line for E naught, but I will draw a comparatively small line for I naught. I naught will be like this, a smaller line than E naught. And why I have drawn it here? Because we have shown it that I is 90 degree behind E naught. It is 90 degree behind E naught. It lags behind, current lags behind the EMF by pi by 2. So this was all about this one, inductive circuit. Now the next we are going to do capacitive circuit. Capacitive circuit. Next topic, we are on page number 14 of your notes. AC circuit containing only a capacitor. AC circuit containing only a capacitor. Only a capacitor. Now, in the same way as I have drawn here, AC circuit containing only an inductor, there was an AC voltage source and there was an inductor. Now I am going to draw an AC source but a capacitor in place of inductor. Capacitor is C, value of capacitor. This one we generally take left one as positive terminal and right one as negative terminal, and E is equal to E naught sine omega t. With the help of this, E is equal to E naught sine omega t. Now again I am going to derive a relation for current I. Okay, and then we will see that whether current is lagging behind the voltage or current is leading ahead the voltage, that we are going to see. So as shown in figure, consider a pure capacitor C connected across a source of alternating EMF E given by E is equal to E naught sine omega t. Due to continuous charging and discharging of the capacitor plates, a continuous but alternating current exists in the circuit. What is the work? What capacitor actually does? What capacitor actually does? Capacitor, the main work of capacitor is to get charged and is to get discharged. So it gets charged and discharged. So the battery which we use is made up of capacitor. If there wouldn't have been any capacitor, then the concept of battery will not actually work. Battery contains capacitor only. So capacitor stores charges in itself. Okay, so due to the continuous charging and discharging, the capacitor plates charge and discharge alternately because it is an alternating current. So potential difference across the capacitor plates at any instant potential difference across the capacitor plates is equal to applied EMF. Applied EMF. Potential difference across the capacitor plates is V and applied EMF is this E. And what is this E? We know that E is E naught sine omega t. Please mark it equation number 1. But V is equal to Q upon C. What is the relation between voltage and capacitance? V is equal to relation between voltage and capacitance is V is equal to Q upon C. It implies that Q is equal to CV. From equation 1, Q is equal to C, and what is this V? V is E naught sine omega t. C E naught sine omega t. Current at any instant is, as we know that current at any instant is I is equal to dq upon dt. It means that d upon dt, what is this q? Q is C E naught sine omega t. So I have kept the value of Q from here, C E naught sine omega t. I is equal to d by dt of C E naught sine omega t. Is that clear to you till now? Is this clear?
Yes.
Okay. So I is equal to d by dt. Actually, this is the formula of current. Current is I is dq upon dt. So what I have written d by dt, and in place of q I have written this one, C E naught sine omega t. Now we will be differentiating this C E naught sine omega t. So I is equal to C E naught is constant. What is variable term? Variable here is small t, and we have sine omega t here. So sine omega t is the variable term because it is containing small t. C E naught is constant, so C E naught, and sine omega t. What is the differentiation of sine omega t? Sine omega t is cos omega t. And what is the differential of omega t? Differential of omega t is omega, as per chain rule. So I will be written as omega C E naught cos omega t. So here again we have got this relation for current, but again I want to convert this cos into sine. So if we do sine 90 minus theta, then it will not work for me here. Why? Because it will deliver a negative result, but I don't want a negative result. Let's check it with the last derivation. What we have done in the last derivation, we have converted this cos omega t to sine omega t. How? This one, cos omega t, I have written sine 90 minus omega t. Sine 90 minus omega t, but I want omega t to be written at the first place. So to bring this omega t at first place and make it a positive omega t, what I have done, I have taken this negative sign common, and this served two purposes for me. What it has made, by taking negative common inside the bracket, it has made this omega t positive. So omega t has become positive, and this sine minus theta is minus sine theta. Then minus sign comes outside and it gets multiplied by this minus sign. So the value of current becomes positive. So I want the value of current to be positive, and I want this omega t also to be positive. So in this capacitor case, I cannot write sine 90 minus omega t. Okay, so what I will do here, I will write sine 90 plus omega t, because sine 90 plus theta is also cos theta, and sine 90 minus theta is also cos theta. So what I will write here, sine 90 plus theta. So I is equal to I is equal to, what is this? Omega C E naught, omega C E naught sine 90 plus omega t. Sine 90 plus theta is also cos theta. So I is equal to E naught. I want to know the value of I naught also. So E naught, actually I naught, what is I naught? I naught in the case of resistance, it is E naught upon R. In the case of inductance, it was E naught upon omega L. So E naught divided by something, E naught divided by resistance will give me current I naught. So how I will write this one? I will write E naught upon 1 upon omega C. E naught upon 1 upon omega C. So in the case of capacitive circuit, this 1 upon omega C will behave like resistance. In the case of inductive circuit, this omega L behaves like resistance. Is that clear to you? Is that clear to you?
Yes, sir.
Okay. And this one is called resistance. This omega L is called inductive reactance. Reactance is also a new term given to resistance. Its unit is also ohms. Its unit is also ohms, just like resistance. So omega L is called inductive reactance. So reactance is also used for resistance only. In the same way, I have written E naught upon 1 upon omega C. This one is called what it was. What we call it? We call it inductive because it was the case of inductance, which I have done on the last slide. Inductive reactance. And what is this 1 upon omega C? This is capacitive reactance. Capacitive reactance. Okay, and sine, let's write omega t at the first place and pi by 2 at the second place. What is this E naught upon 1 upon omega C? This is I naught in this case. I is equal to I naught sine omega t plus pi by 2. This shows that current leads the voltage by pi by 2 in a capacitive circuit. Is this clear to you, Anusha?
Yes, sir.
Okay, now come on page number 15. Again, we are going to draw these two diagrams as we have done in inductive case. First, we will draw a graph between E and I versus omega t. Then we will draw this phasor diagram. Okay. This is E. E is equal to E naught sine omega t. So this one is, what is this angle? 0. This is pi by 2. This is pi. This is 3 pi by 2, and this one is 2 pi. 0, pi by 2, pi, 3 pi by 2, and 2 pi. And what I have seen here is that I is equal to I naught sine omega t plus pi by 2 means current is leading ahead of EMF by pi by 2. Means current has started earlier. Current is ahead of voltage. Current is ahead of voltage. It means that current has already started from minus pi by 2. That's why when EMF was at 0, current has already been started from minus pi by 2. So now I will draw it like this. Is that clear to you? So this graph is of I. Graph between E and I versus omega t. E and I versus omega t. Clear? Is that clear? Are you there, Anusha?
Drawing the diagrams for what is this
Okay, okay. Done?
Yes, sir.
Okay. Graph between E and I versus omega t. Now we are going to draw phasor diagram for a capacitive AC circuit. So for a capacitive AC circuit, for a capacitive AC circuit, so in a phasor diagram we write Y on the y-axis and X on x-axis. We always draw E naught here in the first quadrant. This is E naught, and in this case the current is leading ahead of this EMF by pi by 2. So it is leading ahead by 90 degree. That's why I have drawn current ahead of EMF. Clear? Anusha, clear?
Yes.
Okay, so it's enough for today. We will do it later on tomorrow at 9:30 p.m. Okay, and I will try to complete this chapter in 2 or 3 more classes. Okay, by Monday, Tuesday, Wednesday, I will try to finish it. Okay.
Okay.
Okay, Anusha. Good night.
Okay, sir. Have a good day.
Okay.